Good afternoon, and thank you for joining this webinar. And as Lisa said, in the download section, you can download this presentation. There's quite a bit I'm going to cover in a short amount of time. I have sprinkled also some QR codes throughout this. You can take a picture on your screen if you want to learn more about something. And in the downloadable copy, there will be hyperlinks to resources as well. So let's begin. Of course, it doesn't want to advance, but we'll get there in a second. Okay, sorry about that delay. So we'll start with the basics. There are two known sources to remove contaminants from indoor spaces: ventilation for dilution and removal with some type of filtration. Most common is mechanical filtration that's been used for a long period of time. But what are we trying to do when we're trying to remove these sources? We're trying to remove mass from the indoor space by replacing it with ventilation mass or removing it through filtration. And so we need to understand, we're talking about the mass flow rate. Things that we measure in airflow and we specify in airflow typically are actual volumetric flow rates. And we're going to explain why the mass flow rate is important in this equation. So what are we trying to remove from the indoor space? There's all sorts of things that are in the air. And this chart here kind of shows the differences of things that are in the air. And we have to be concerned really about the things that are 10 microns and below, where you can see the coarse bar and the fine bar at top and the very fine. Those are things that can get deep into the lungs. And there are things that you cannot see with the naked eye. So we don't really know that they're there, but yet we're breathing them in. This illustration does a good job of showing where things can happen within a space. It depicts a home, and one thing to know is spaces are completely different. One office space is different than another office space. A home is different than an office space. There are similarities for certain, depending upon the materials used for construction, but the processes that are happening in the space determine what's going to be floating around in the space. And some of these things, as the smaller we get in the size in microns, the longer this is suspended within the air and floats around and can travel through the HVAC system, and that's where we can remove it with filtration, or we can push it out with dilution. Some objects settle on the ground, but they can also be resuspended into the air. So just because it has fallen to the ground doesn't mean you cannot breathe it in, because just by vacuuming and cleaning, dusting, walking, or other activity can make it reappear and you can swallow it. Breathe it in and it can get deep into your lungs and cause a problem. So we are surrounded by microbes, millions and millions of microbes around us. Some of them are healthy, some of them are not so healthy. Fungi, we eat mushrooms, yeast. I love yeast because I love beer and I love bread. It's used to make wine, but mold not so much. Mold can cause a lot of asthmatic problems and everything else. And it's really said that if a young child has a dog nearby as they grow up, they may actually have less chance to develop allergies because they're exposed to these things early on. The challenge is, of course, again, we can't see these microbes. They're hidden beyond us. And the human's body sheds probably about 30 to 40,000 skin cells a day. It's amazing to think that there's that much floating around. And the dust itself is a collector or a reservoir for bacteria and viruses. It's amazing that in hospitals, there's no requirement to filter the return at the source, at the operating room or at the 6-person room. We only filter it, the clean air going into the space. A smart person would filter it so the ductwork wouldn't get dirty, and thus other things would stay in that ductwork. So this document from the National Academies for Microbiomes in the Built Environment spells out how ventilation and filtration are very good at controlling the sources. Certainly humidity and moisture have a big impact on the ability of these microbes to survive and thrive within the space. So we're talking about ventilation again. We're talking about moving air. We're talking about the mass. And we look at the relationship between mass, volume, and density. These two jars that Lisa created shows a very good example of that. The jar on the left has more mass in it and then the jar on the right, but they're both the same volume. So thereby the density is going to be higher. Well, how does this affect ventilation and airflow? Well, air is a mixture of gases, and it's going to change with altitude, and it's going to change with pressure. So as you rise in altitude, the density is going to get lesser. And as the temperature goes up, the density also is going to decrease. So our dilution flow rates are expressed in volumetric flow rates. The flow rates that are in 62.1, 62.2, 170, the IMC, the UMC are all expressed in actual flow rates, but they're tied to standard conditions. They're standardized, and these are the most, this is the most common standard conditions that there is, 70 degrees at sea level, at 0% RH, dry air. And when these conditions are different than what is the standard conditions, then we have to make the adjustment to have the same dilution or removal effect from the airflow. And I'm going to show you an example. So there was an addendum J that was passed last year that requires now engineers to make adjustments for cooling densities because it is much warmer, especially at altitude. And this is going to show you, so in the green at sea level, we have 0.0575 our density, pounds per cubic feet, and the cooling and heating design level at 70 degrees, and then the 0. Now, as you can see, there's not much of a change in moisture between the density levels, so we can discount moisture. In fact, most moisture sensor or humidity sensors aren't accurate enough to resolve that problem. But there is a significant change with the densities with elevation and with temperature. And if we replace the density with actually airflow, you can see how much it changes. So for example, if we are looking at Colorado Springs at a cooling design temperature of 90 degrees, you can see that the minimum ventilation is 24% under what it would be at sea level. So if an engineer is making an adjustment ahead of time for this, there's a challenge. If the balancer isn't making his adjustment to his instruments, then it's not being balanced correctly. So we have to make sure we carry this all the way through the process, or you use an instrumentation that is always measuring a mass flow and controlling a mass flow, and that will solve the problem. Now, on the flip side, even though Edmonton's at a higher elevation, in the wintertime, it's quite cold. And you actually have more ventilation air by using volumetric airflow than you would by using mass airflow. And you could use this actually as a smart ventilation approach. So it's a lot more expensive to heat up cold air than it is to cool down air to room temperature. So you can do some smart ventilation by maintaining, if you want, whatever the ventilation you want, whether it be minimum or something over minimum, by using this equation. But controlling airflow is more about ventilation. Here's a pressurization equipment. Now, pressurization in a space or in a building is the differences of airflow rates. Whatever goes in versus what goes out is your pressurization airflow. But however, if your temperature going in is higher than your temperature going out, then you're going to have a difference in density, and it's going to affect your pressurization. So it's important to understand what the flow rate going in and what the flow rate going out, and more importantly, what the mass flow rate is in order to determine. Of course, pressurization, if you are negatively pressurized, you can bring in moisture, dirt, and heat or cold air that isn't tempered. The best way to bring it in is through the air handling unit where it's filtered and conditioned. You don't want to bring it through the window or the front door, which often happens. And the dew points are constantly changing. We're evolving as a geographical map here. We are rising more and more moist in the Northeast than it ever has before. And they're seeing a lot more moisture with the monsoons and everything in Arizona or the Southwest as well. So it's important to maintain that pressurization, especially in those areas that are dark brown through dark red. And another thing we have these days, we have wildfire smoke. It travels quite far. There'll be wildfires up in central Canada or western Canada, the mountains that would travel down the East Coast. And we're all exposed to, and we've all experienced it in recent times. What's happening in the smoke is you've got VOCs in the smoke and you got particulate matter, and it's best that you want to filter those things out in the building. A lot of people will say, well, let's shut off the outside air damper completely, and that's the wrong approach. And guideline 44 that was released addresses that as well. You want to keep pressure on the building. You want to try to maintain ventilation to try to again dilute what's inside the building. And you want to make sure that your exhaust is not greater than your supply or your ventilation into the building. Otherwise, you're going to be negatively pressurized and you're bringing in smoke through the front door, go through cracks and crevices in the building. Also, when with Standard 241, which we'll address a little more in this presentation, pressurization is very important, just as it is in healthcare spaces. So you aren't providing air that has contaminants in it, bioaerosols in it, that are getting people breathing into a space that's supposed to be clean. You want the air to go from a clean space to a dirty space. And of course, buildings themselves are dynamics. HVAC systems within buildings can fight each other. The higher the number of floors, the more the stack effect. You can have stack effect as little as four floors. I mean, everybody that has a chimney on the house can see stack effect in action all the time, depending upon what the outside air temperature, and then you have a wind pressure outside. And a lot of dynamic things are always happening. And because of energy savings, most of our systems are dynamic. Most fans, even if they're constant volumes, have multiple speeds and always having an effect on the pressure of the building and the ventilation rate into the building. So the first ASHRAE ventilation standard was put forth in 1973, and it covered both ventilation for commercial and residential. And the important thing to note here is it's for spaces that occupy humans. When we're talking about buildings, we want to provide comfort and well-being to the people inside the buildings. Energy should be a secondary thought. We should be maintaining the health and well-being of the building, of the people that are in the space first. And in this very first edition of ASHRAE 62, it talked about clean ventilation air to remove the contaminants in the space, such as carbon dioxide or other things in the space, and bring in more oxygen or displace what is in the space that is bad. But this is a new concept. In 1859, Florence Nightingale published her notes on nursing. And she had her very foundation of the rule of nursing. The first part of rule of nursing was ensure that the patient was well ventilated and he was kept warm and it was kept clean. That cleanliness and ventilation are hand in hand. And she really addressed the need for bringing as much fresh air as possible and make sure that you knew the direction of air, just like we do in ASHRAE 170. We want to make sure we're moving clean the dirty and not taking someone has tuberculosis, moving the air over him and bringing it to someone else. So not a new concept at all. She had direct experience with this during the Crimean War, where she saw people were dying due to conditions of their hospital, not due to the wounds that they sustained in battle. So an interesting trend that we've had is the ventilation rates since Florence Nightingale's time in 1859 till now have consistently decreased. We're really at a low ventilation rates, and we are constantly decreasing these ventilation rates in the name of energy. And I just wanted to make you aware of this. Believe it or not, during the 1900s, 1900 and 1920, 40% of the states in the Union had ventilation laws. There were laws in the state books for ventilation. Now we have a building code. We don't have the laws anymore. And those ventilation rates were twice as high as what we had today. As you can see, the dip in 1981, well, that was after the Department of Energy was formed in 1975, and the first, the Department of Energy was formed in 1977. The first ASHRAE standard for energy was 1975. And ASHRAE made a decision to drop the ventilation significantly at that time. Well, that resulted in, unfortunately, sick building syndrome. So we don't want our buildings killing us. And there are two things that we deal with. Sick building syndrome, you don't know what the etiology is. You don't know the known reason for this, basically, but you do have odor, you do have high levels of CO2, which both indicate that there's low ventilation rates. Where a building-related illness could be like COVID-19, or it could be mold, or something else that's in the air that's a known thing, and that you can resolve. These are all the microorganisms that can travel through the air and infect people. There is quite a few of them, as you can see here. Some of them are less common than others. I had never even heard of a HPS when I put this slide together, and a couple weeks after I put this slide together, Betsy, Gene Hackman's wife, had passed away from HPS. They had rodents in the house. It's not known whether it's with direct contact or through the air, but these things are impossible. So it's very important to make sure that the space is well maintained, that you don't have moistures. ASHRAE has recently set requirements for moisture at 59 degrees dew point as a max or 60% RH. And it's very important because it will help grow the stuff. And again, filtering out the air. If we filter air well, if we do dilute the air well, we can mitigate these problems that can be in the air. We've had an epidemic this year with measles, a breakout throughout the country. And measles can be eradicated through immunization. However, there are some people that are immune compromised and they can't even have an immunization. So it's very difficult. So we have to protect those people. But as we have seen, it can spread very quickly. Measles is one of these things that can stay in the air well after the people who had the measles left the space. And it's one thing I don't like about ASHRAE 62, for the purposes of energy, it allows you to shut off the damper to a space and shut off the ventilation to a space when it's unoccupied, even during occupied periods. I think we should be ventilating all the times during occupied periods, just in case someone left something behind. Tuberculosis is also kicked upward. It's been a downward trend for quite a while, but I just wanted to show you because it is kicked upward. And this year we have a significant amount of greater hospitalization in influenza than we've had in the past several years. So it's quite a big number. So these are all things that spread through the years, things that we can be concerned about. And as people work in the HVAC industry, we can do a good job at trying to control them, properly filtering and ventilating things. So when we talk about ASHRAE 62.1, we're talking about what's acceptable in the air, right? The purpose is to specify minimum ventilation rates. Many people treat these minimum ventilation rates as a maximum, like a speed limit. There's no reason that you have to treat them as a speed limit. These are the minimum recommended rates to create a so-called healthy space. But the so-called healthy space is based on a space that has no known contaminants that satisfy a majority of 80%. So basically we're saying, well, maybe 20% of the people get sick or 20% of the people are uncomfortable. That's okay, but that's the minimum. So if we want to do better, we can do better. In ASHRAE 62.1, we're looking at what's in the space. Well, we look at normal contaminants in the space, things that we can assume that are going to be there in the space based on the materials in the space. But for an office, we don't consider anything really related there, any significant level of contaminants. In a classroom, there may be some small bit of significant related contaminants, maybe glue or paste or paints or chemical stuff in a chemistry class. And a lot of these things are source controlled as well. The same thing with electric classrooms. What I'm trying to note is we're not considering all the contaminants when we're talking about the minimum ventilation rates. There's a lot of contaminants that are in the space that we're completely unaware of. All those things that I had on the table before, all those things are in the Why Indoor Chemistry Matters handbook that you can access. So ventilation air is a combination of the recirculated air plus the outside air mixed together, and it gets more complicated in a multi-zone system. An air cleaning system is something that's going to remove the particles that are in the air or other gases through absorption through the air. And this is basic. This is out of 62.1. This shows what a ventilation system looks like. It's pretty much been the same for multiple iterations of the standard, but there's been a couple more filtration units that are added. As you can see, there's filtration units everywhere. If you don't know how much airflow is going through the filtration, then it's hard to understand the effectiveness of the filtration. The interesting thing about 62.1, again, 62.1 is a minimum standard. So the minimum requirement in 62.1 is a MERV 8 filter, only where there's a wetted surface. If you have a heat transfer device, such as a heater, and you don't have any condensation, then you don't even have to use a filter, according to the language in 62.1. I think it should be much higher, but 8 is where we are at. In the IMC, it only says approved filters. There is no requirement for a minimum. There was a requirement that was put forth for the next version of the IMC for a MERV 13 filter. Unfortunately, the ICC had voted this down. They got some suggestions from concerned people that MERV 13 was a little too high, so we're back to not having any requirement. But there is a basis for this, and in California, Title 24, they seem to really care about the health of the people inside the buildings. They're not only concerned about recirculating air in the space, but they're also concerned about the outside air being filtered through this filter. Because of course, there is some smog in California, and they've had a lot of wildfires too. So MERV 13 filter do a very good job of removing the particulate matter from wildfire smoke, smog, and of course, anything else that I showed in that chart that's in the very fine category. So when we're looking at the mechanical filters, this is the shape of the curve. So when we looked at like COVID-19 or the SARS-CoV-2 virus, the virus particle size was 0.10 microns, but the virus itself didn't travel naked through the air. It traveled in with your moisture from your mouth, whatever is in your spit, and some other proteins that are mixed together. So it's a little bit larger. But you can see why there's a recommendation for MERV 11 at a minimum, or MERV 13, because it does a very good job of removing smaller particles in the range of 1 to 3 microns. And really, it's that 1 to 3 micron, which we're learning more and more about, is very detrimental to the human body as it gets in the blood, and it can get down into the bloodstream, and from there it cause long-term effects. A thing to point out is it doesn't take a very large bypass. We have to ensure that the filters are well fitted for the filter holder, and that they're tight and there's nothing obstructing them, because a small little bypass that's going around the whole circumference of a filter that equates to 0.75 of an inch can take a MERV 10 and bring it down to a MERV 8. So it's very important to ensure that maintenance is maintained and it's a good fit and the right filters are used in this process. So when we talk about filters, there are two standards of filters. So we start with subtractive technologies. And subtractive technologies are these mechanical filters I've been talking about, the MERV-rated filters and the HEPA-rated filters, things that capture things in the airstream directly. And then you have sorbent media that will absorb gases, such as perhaps formaldehyde or CO2 or something out that's in the air, whatever you're trying to remove from the air. And then you have UV light. UV light has been around for decades and very successful at killing things and activating viruses and so forth. There's upper room UV and there's direct UV in the HVAC system that does a very good job. But recently there has been a push for additive technologies. These additive technologies have a bunch of different technologies that have come to being. And this new technology doesn't have a lot of science behind it yet, or not a lot of testing. Certainly the people that develop the technology may have a lot of research, and it's important that when you're reviewing the technology and determining whether you're going to use the technology, that you do your own homework and understand what's in play here. And that's why I'm doing this presentation, to show you that there are multiple things to consider. Ozone by itself, which is the O3 on this table, is naturally occurring. Every time there's a lightning storm, there's more ozone created. There's ozone in the atmosphere. And it's very good at removing poisonous UV rays from the sun, right? However, ozone with the indoor space has a negative effect to health, because it changes the indoor chemistry. It interacts with different things that are floating around the air, different chemicals in the air, different VOCs in the air. And it also reacts with oils on the person's skin and can cause multiple reactions. Hydroxide radicals, the OH right here, are something that are floating around and they're byproducts of ozone and other things that are happening in the air. Photocatalytic oxidation, or PCOs. If you read some literature about what these products do, the literature will say, well, you clean the air and you produce CO2 and water vapor. and pretty much that's it. However, there are other things that can be produced, and there's some PM that can be produced, and some semi-volatile VOCs or VOCs that can be produced, and some ozone which can interact in the air. So have to be aware of that. Mechanical filtration pretty much does a good job removing everything but VOCs. Ventilation pretty good to remove everything, but it can add ozone to the space because the ozone may be higher outside. It can add PM if the PM is higher outside and you don't filter it well. And then you have to be aware of the ionizers and plasmas and fogging and the UV and the impact that they have here. There's more information, as I said, on this 3D barcode. So because of the concern, ASHRAE publishes this emerging issue brief just last year on different reactive species in the air. I recommend you taking a look at it. It's very scientific, but there's a lot of chemistry that's going in, and we really haven't learned that much about indoor chemistry. It's still a very new science, and most of the chemicals that are inside, that are in the air, we don't even know much about. The HVAC world is much different than the healthcare world when we're making medicine. There's a lot of unstudy of what's going into medicines and what chemicals and what the effects are on people. But in the air, it's less so. Here's some studies that are showing that there may be some byproduct formation from different technologies. And some, even with UV, UV can act, even though it's a good thing, it can kill things in the air. Sometimes it reacts with other things that are in the space. So NIST actually did a study where they put some UV in the bathroom, and they found that the urinal cakes were off-gassing some VOCs, and the UV reacted with it and caused more complex VOCs and particles to evolve, generating some particles. So we have to be aware, as I would like to say, measure twice and cut once. Ensure you understand what it is that you're putting in the building, what you're using, if it's beyond standard ventilation and regular filtration. So CO2 has been used for a couple of centuries to understand the ventilation rate. And CO2 showed up in 1989, really for the first time. And in 1989 standard, they talk about 1,000 ppm being a value that should satisfy odors. Well, since that time, CO2 and DCV, CO2 DCV has been misunderstood. I'm just going to quickly try to clarify, but CO2 is directly dependent and independent with ventilation. You can't change the ventilation rate and not have an effect on CO2 unless you have something adding or removing CO2 that isn't people. And so by using algebraic equation, you can actually determine what the outdoor airflow rate per person is. However, if someone says, hey, I have 1,000 ppm in the space of CO2, you cannot know the ventilation rate unless you know some more about the equation, what the number of people, what the generation rate, and so forth. So there's more that needs to be solved. And ASHRAE, based on some document that was published about 8 years ago by Andrew Pearsley and NIST of how to calculate CO2, we published a new version of 62.1 for DCV. It's called Addendum AB, and I'm going to review that quickly here. So you can see that we have all these different spaces, all different breathing zones, and we have default delta CO2 limits. So the assumption is the outside air is about 400, it may be 350, it may be 420. But if you take 400 or 420 as a minimum and add this delta limit, then you'll get to the true limit. So as an example, a conference space at 1,500 delta CO2 plus 400 outside gives you 2,500 ppm. And an auditorium is 2,200, much higher than 1,000 ppm. So 1,000 ppm certainly does not apply to all spaces. There's also an occupant density adjustment in this. In ASHRAE 62, we have default occupancies in the tables. If you know the actual occupancy, you have to make an adjustment, otherwise you can come up with the wrong steady state value. There's also recommendations of sensor placement and calibration requirements. You have to have a sensor in each ventilation zone that's going to be using DCV. Especially as a multi-zone system, we have different, like a conference room and an office feeding off the same air handling unit or DOAS unit. And the specific control requirements to reset the CO2 and the ventilation based on the CO2 level. Basically, so if you have an unoccupied space and you walk into the space initially, the CO2 should be close to outside ambient of 400 ppm. And as the CO2 rises in the space, you should be opening up that outside air damper. In the past, it was controlled by a limit. And people would wait until the CO2, say, rose to 1,000 or 1,200 parts per million before they opened up the outside air damper. And because CO2 is lagging and it takes a while to fill up the space, you're underventilating the people for 30 minutes to up to an hour, depending on the space type. In an office, that could be up to 5 hours because the population density is so low. So this is looking at some of the spaces with addendum AB and what the steady state values are. You can see an office is at 17 CFM, and an auditorium is at 5 CFM per person. The most densely occupied spaces have the least amount of ventilation, and they're going to have the highest steady state CO2. So if you would take a conference room, which is 6.2 CFM per person, and about 1900 ppm steady state, and you tried to control this at 1,000 parts per million, you're going to ramp up your outside air to try to bring in 17 CFM per person, unless you are measuring and limited. The best way to do is limit the minimum, so you can't underventilate, and limit the maximum, so you can't overventilate and waste energy. And you can do this with airflow measurement, of course. Metabolic rate, the action that people have, the movement that people have, generates more CO2. So it's very important to know metabolic rate. The metabolic rate of someone sitting watching this presentation right now is probably pretty low. But if you're on a treadmill watching this presentation, you're going to have a much higher metabolic rate, closer to 3 or maybe even higher. The effect of that, just by looking at the value of 1,000 parts per million, you can see it's going to go from 17 CFM per person in an office space all the way up to about 65, 66 CFM per person. So it's really important to understand the metabolic rate as well as the space type and how it fits in with the minimum ventilation requirements of ASHRAE 62, which translate directly also into mechanical codes. Some of these additive technologies add or remove CO2. This technology removes 50% CO2. This technology removes 10 to 20% of CO2. This technology actually adds CO2 to the space. You cannot use a technology that adds or removes CO2 and DCV. In fact, you're not even supposed to be using the indoor air quality procedure and DCV together, because DCV is part of the VRP. And I'll show you why this. But there is a requirement in here, and it's been in the standard for quite a while. So I'll calculate steady state. So we're at respiration quotient. This is basically based on the diet, and it's going to change if you're in Asia versus in America, or if you're a vegan versus a meat eater. Basal metabolic rate is basically the level of energy that we need to keep the human body alive. The metabolic rate I just covered, and that's on the table on the right here will show you different metabolic rates. And of course, CO2 is a gas, so Boyle's law, it's going to change with temperature and pressure and density. So we take a middle classroom, and we calculate what the generation rate is, and we use the 62.1 IMC requirements. We will calculate a ventilation rate outdoor of 470 CFM, or 13.4 CFM per student. And then we will calculate a steady state value of 1,129 parts per million. However, if you have something that is removing the CO2 in the space with a 30% removal, then the CO2 is going to be reading 790 on your CO2 sensor. And your HVAC system instead is going to think that you are bringing 25.7 CFM air when you are not. And if you're trying to control DCV, then your DCV may not even be activated. It may not even move off the minimum setting. It's always good to measure the air and know what you have. When we talk about the indoor air quality procedure, we have a table in the IAQP, but you must understand these are levels of harm. ASHRAE didn't make up these numbers. They went to different sources, and these sources are based on outdoor air levels. If we look at PM 2.5, for example, That's 12 micrograms per cubic meter. That's the EPA actually dropped that to 9 as a limit for the year. And if we look at formaldehyde at 33 micrograms per meter, most cleaning solutions or absorbent solutions using the IQP will use this because it's very low value, and it is usually a determining factor in that. However, it doesn't take much PM, it doesn't take much formaldehyde to cause harm, to actually cause long-term effect on the human health. This was an article published in the ASHRAE journal that shows the cost of this, where we're doing more damage than we should be by designing through the IQP or designing at a minimum. Maybe we should be providing more ventilation than what's recommendation. And these are the levels of harms that you have within the space. Some contaminants, PM and PM 2.5, and nitrogen dioxide, which can off-gas from cooking, and formaldehyde, which can come from building materials in the space and radon from the earth. These are all things that cause long-term harm to the body, and we should be aware of these, and we should be doing everything we can to remove them and dilute them. As I said, most IAQP calculations are driven by formaldehyde. However, everything is based on first pass efficiency. Things degrade over time. So if the efficiency drops to 60%, then your formaldehyde concentration may raise up to 42 micrograms, which is above the limit. And the challenge we have is it's a one-time test that's required by ASHRAE after the building is occupied and built. And the formaldehyde sensors that you have that you can buy to build on the wall aren't sensitive enough. This has an accuracy of 20 parts per billion, where 25 parts per billion equates to, 20 parts per billion equates to 25 micrograms per meter cube of formaldehyde. So these sensors, though they're evolving, they're not quite sensitive enough to work in real time. So ASHRAE 241 when it came out in 2023, it had a novel approach. It's a rate-based standard. It's looking at the ventilation rate per person. It's looking at providing a clean equivalent airflow rate per person. Understanding what the airflow rate is. If you're using an air cleaning system in the building, then you have to know what the clean airflow rate is. You have to ensure that the clean airflow rate of that system is behaving as it was designed. There's a building readiness plan, and building readiness plan, anybody that owns the building or the local AHJ or health official can determine when you go into IRM. And the plan has to be very complex to include, have you tested all the modes of operation? As I said, most buildings are multiple speed. They have dynamic controls. Have you tested that you have the right pressurization under all these dynamic controls? Have you ensured that your outside air is providing the right amount of ventilation and to all the spaces as well? And there's a lot of functional performance tests and commissioning that's required in this standard. And this is just to show you that if you look at the minimum ventilation rate and compare it to the equivalent clean air rate in 241, an office isn't so bad. It's fairly easy to achieve. It's only twice as much. Electrohol, on the other hand, is 6 times greater for infectious aerosol, and the convention center is almost 10 times greater to remove infectious aerosol. So if there's another breakout of infection aerosols, you don't want to be in a highly occupied space unless they have really good air cleaning and really good ventilation. And so this is explaining what the filtration requirements are. And this is a similar diagram to what's in 62. This is the 241 diagram. And it shows you all the paths where you can have air cleaning. You can have air cleaning in the space, which is good source control. But there's lots of air cleaning systems you can tie that are just recirculating systems. But if you don't know the rate through them, then you cannot prove how they're working. And now there's a requirement these things should be tested independently, and you should verify in the field. As the last sentence says, if no air is flowing through, then your VAS shall be 0. Your effectiveness is 0. You don't have any clean air provided by this. This calculator I'll quickly show you. An office, we fail at 62.1 rates, but if we double the airflow, we can easily take care of an office, and that's probably very achievable of an office. Or we can improve, we keep the airflow at the design minimum and just improve with the filtration to MERV 11. However, if we look at Another type of space with electrohull, you can possibly get there by doubling the airflow. We went from 6.2 CFM to 12.4, and we need 50 CFM per person. So we have to include add MERV 13 filters and 3 air cleaners in the space and double the airflow, or we have the opportunity to drop the number of occupants down. And that's one of the benefits of 241. Well, that's my presentation on equivalent clean air, and I'm happy to answer any questions that may have come about during this presentation. Thank you for listening.